So in this lecture, we will talk about how to solve dynamic problems. Problems where we worry about wave propagation or we worry about the acceleration term in an elastic problem. And so let's first consider what is the governing equation, which is the conservation of linear momentum. And so your undergraduate kind of level of this is just to say that F is equal to force is equal to mass times acceleration. But we're going to write this for a continuous body. So let's first imagine we have some arbitrary body, which we call its domain gamma, or omega. And then we'll imagine that we have some arbitrary subdomain, so some arbitrary part of the body, which we call omega 1. And we'll also need to know the boundary of that is gamma 1. We don't really need to know it, but the boundary we'll say of the overall body is gamma. And so, similar to what we did for the static case, we're going to compute the sum of forces acting on the arbitrary domain. So F, the forces acting on the arbitrary subdomain, are the integral over the body times any body force plus the integral over the boundary, well this isn't the subdomain, the integral of the boundary of the traction, like so. Now, of course, we know that this is equal to an integral, this one stays the same, and the second one, the traction is equal to the normal direction added with the stress, integrated over the body. This, we can now apply the divergence theorem, and we can write the second term to be, the first term again stays the same. The second term now becomes an integral over the body, or the subdomain. And now we get the divergence of the stress integrated over the domain. And so the total force now we can combine into one integral as being the body force plus the divergence of the stress integrated over the domain, like that. So that's the left-hand side. That's no different than what we had in the static case, and in fact in the static case we would simply set that equal to 0. So the only missing thing is the equation for MA. So MA is really the acceleration of the center of mass of this subdomain, and we write that as an integral over the subdomain of its density. So if I just integrated this, that would give me the mass, but then I have to integrate the acceleration, and just to differentiate it as a field, I'm going to just write it as the second derivative of the displacement as a function of x. We'll get used to the idea here, this is actually a function of x and t now, integrated over the domain. Okay? And so now, to write f equals ma, I have f, and I have ma. We notice that they're all integrated by the same subdomain, so I can combine this all in the same integral. And so f equals ma becomes the integral of rho density times acceleration minus body force minus the divergence of the stress is equal to 0. This is an integral over any arbitrary subdomain. And because this subdomain was arbitrary, I could move it. I could take this subdomain, or I could take this subdomain. Because I could take any subdomain, if I integrate some function over any bounds and it's always equal to 0, what that tells me is it tells me the function itself is equal to 0. And so my governing equations look like the density times the acceleration is equal to the divergence of the stress plus the body force. And so that's the strong form. course, we have to set boundary conditions, and the boundary conditions for this are a little different depending on how we want to define it. The first boundary condition is that we'll say that the velocity is equal to a prescribed velocity on a velocity boundary condition. So this is very much like a displacement boundary condition. On the other hand, we're going to say that alternatively we can say that the traction is equal to a prescribed traction on the traction boundary condition. So this is our essential boundary condition, this is our natural boundary condition. The natural boundary condition is no different than the static case. The essential boundary condition is now just a restriction on the velocity. Of course, if I constrain the velocity over all time, I basically constrained the displacement as well. So now we're going to develop the weak form for these equations. And to develop the weak form, we multiply the strong form by an arbitrary test function. So that's W times rho acceleration times density. I'm going to move it all onto the one side again, so now this becomes the divergence of the stress minus the body force integrated over the domain is equal to 0. Now, since we've already done it for the static case, I'm going to do this a little quicker this time. So the first and third terms stay put. We're not going to integrate those by parts, they'll just stay. So let's write those out first. So we'll move this to the left-hand side. So we'll have the test function times the density times the acceleration, which is a vector, integrated over the domain, is equal to the right-hand side, which is all the force terms. And so this term is just going to be the body force, so let's leave that. Omega dot body force integrated over the domain. And then this one is the one we have to play the trick on. And so what we're going to get here is when we take, so this would be positive on this side, but after integration by parts, the term that's left over is going to look like this. The gradient of the test function dotted with the scalar product with the stress, that's integrated over the domain, plus the part that's going to be, we're going to apply the divergence theorem too, so this is an integral over the traction boundary of the test function times the applied traction integrated over the traction boundary. And so that is the full weak form. I skipped some steps in terms of doing the integration by parts. I also applied the fact that we set W to be equal on the essential boundary, so I only considered the part of the boundary in which we prescribe traction. And so this is our weak form. Now, if the problem is linear, this term is going to give us something like a stiffness matrix. Once we recognize the fact that the stress is just the elastic tensor times the strain, which is just the displacement, or the gradient of the displacement. These two terms are exactly like the external force that you get in a regular finite element method. This is the new term, so this is the term that we're going to look at first. And so the next thing to do is to consider our discretization. And so for the discretization, we need to be able to discretize U and W. We're not going to discretize time yet. So we'll say that U is equal to N, the right order first. U is equal to dI Ni. Strain is equal to B, okay, that's not a B. Strain is equal to BI dI. So this is, again, I'm writing it a little shorthand, but this is basically the derivative of the shape functions, but packed in a symmetric storage, and this is going to give me just a vector of the strain components of the symmetric part. W is going to be equal to Wi Ni, and the gradient of W we only care about the symmetric part, is going to be equal to BI WI as before. And so that gives us our discretization. Now what we're going to do is we're going to plug that into the weak form. And so when we have acceleration term, we're just going to take time derivatives of the nodal displacements. Those are still going to be functions of time for now. And so the first term is going to give us an integral of Wi, no dot, we don't need a time derivative there, Wi times Ni rho Nj integrated over the domain times D second time derivative J. So Ni dj gives us the second derivative of U. Wi Ni gives us W. These are really vectors, so the number of components depends on the dimension of the problem. This is going to be equal to, and I'm just going to write this out really quickly, and we'll define the other terms later. So I'm going to say F external minus F internal. We'll talk about those a little bit later. And that is all going to be time dotted with W. So I guess I have to put I, like that. And so I can move everything over to the other side. Well, let's quickly call this something. We call this matrix is the shape functions times the density integrated over the domain. And so this we call the mass matrix, Mij. And what we're going to get here is we're going to get Mij dotted with the acceleration of the nodal degrees of freedom dj minus F external I plus Fi internal. All of this dotted with Wi is equal to 0. And so again, since the test function has to be an arbitrary function, its variables are arbitrary. That means that if I have any vector dotted with any other vector, or a vector is dotted with any vector is equal to 0, then that has to be true for every W of I. What it tells me is that, in fact, this term has to be equal to 0. And so finally my equations are going to be Mij d double dot j is equal to F external minus Fi internal, which if we think about this, this is basically saying acceleration times mass is equal to force, which is where we started from in this whole thing. And so let's just define the last two matrices. So Fi external is exactly the same as what you would get in a static problem. It is just equal to the integral over the domain of the shape functions times the body force, plus the integral over the applied traction boundary of the shape functions times the applied traction. That, so that's the same. F internal is a little different. So F internal is going to be equal to, I have a gradient here. Remember that the stress is equal to the elastic matrix dotted with strain. And if I put these in Voigt form, so in a 2D problem, this is like a 3x1. This is a 3x3, which depends on whether I have plane strain or plane stress. And this is another 3x1. And so what I'm going to get from this is, when I put this in here, this first derivative, remember I'm getting rid of the Wi, because it's going to be, it was arbitrary, so I'm just worrying about the forces. So this is going to look like Bi, so one way to write this is Bi sigma d omega, or I can write it as Bi Ce Bj d omega times dj. So this is basically now the stiffness matrix times the nodal degrees of freedom. So I can do it either way. For nonlinear problems, this is easier to do. For linear problems, I can compute the stiffness matrix once. and then it doesn't change and it just becomes a matrix operation. So depending on what I'm doing, that's what I have.